what those quantum fluctuations are about. So like there's the a muon constantly emits and reabsorbs temporary virtual particles. This entourage affects the muon's magnetic moments or how much torque it feels while moving through a magnetic field. So the simplest quantum fluctuation is the one photon correction, where a muon emits and reabsorbs a virtual photon. This is the most common possibility, so it has the most effect on the muon's magnetic moment. But there's also a small chance that that a virtual photon momentarily splits into a hadron and an antihadron, and the hadron's properties are very difficult to calculate. So this scenario contributes the most uncertain correction to the muon's magnetic moment. And so it's because of this hadronic vacuum polarization that we don't know exactly what the muon's magnetic moment is. And since its magnetic moment is unknown, its G factor, which relates the magnetic moment to the other properties of the particle, is unknown as well. Could you go to the next slide, please? Okay, so basically what we are in need of, since we don't exactly know the muon's G factor, we have theorists' best guess of what it would be, and then we can confirm that with experimentalist findings. And so as of 2020, theorists found that the G factor is 2.00233.186 or 18326. And experimentalists find that it's 2.00233.18416. And so it's the difference of those three last decimal places, whereas the theorists say it's 362 and the experimentalists say it's 416. And so basically what we are in need of at this point is a more precise experiments to confirm this discrepancy and either say that that experimental measure was wrong or that the theory is wrong. And that is what we got on April 7th, just a couple weeks ago, when the Fermilab released their results for the muon G-2 experiment. And they said that they got a G factor of 2.00233.184.122, which is super close to the previous experimental measurement, which is showing that there is likely something wrong with what the theorists are calculating. So they could either be just like making a calculation error or not accounting for a certain correction, which could be an unknown particle. And this discrepancy between theory and experiment is at a level of 4.2 sigma, whereas a level of 5 sigma is required to declare a discovery. So it's not quite there yet, but this is a pretty exciting thing that there could be some physics that we are unaware of. But it's not quite confirmed yet. Like there are theorists scrambling to try to prove that the theory as it is correct. Like they're using new supercomputer methods to attempt to try to create more precise theoretical calculations and clear the discrepancy. But as of yet, no one has done it. So this is a pretty exciting thing that there could be some unknown physics that we are unaware of. So yeah.
Elementary particles. Elementary particles are considered as the most basic particles that form all other substances. However, neither do we know its inner structure, nor do we know whether the elementary particles are composed by other particles. So we do not know its inner structure. Usually we consider like these particles as little like sphere structures, but its actual shape is actually unknown. And it's even possibly cannot be determined. And elementary particles are mainly categorized as fermions and bosons. The picture that you just seen is from a standard model perspective. Standard model is a theory that it describes strong force, weak force, electromagnetic force, and all fundamental particles. It belongs to part of the quantum field theory, a theory that incorporates quantum mechanics and relativity. However, this model, it does not include gravity, so it isn't a complete model. It isn't a theory of everything. So theory of everything is a physics model that science believe that will incorporate that can incorporate everything about this universe at every fundamental structure. But since the standard model only does not contain gravity, so it is not the theory of everything.
All right, next we're going to look at a video of SciShow, which discusses the quarks and some historical aspects as well. So I believe there's a setting for optimizing for the video sharing. Optimize for video clip. All right.
Thanks to Skillshare for supporting SciShow. Physicists strive for simple explanations for complicated phenomena. It's kind of their thing. But 60 years ago, particle physics was not simple. There were dozens of known subatomic particles that all seemed to follow different rules at different times, and nobody knew what to make of all of them. Then a few physicists found the simplicity hiding behind the chaos. Quarks. And 50 years after their discovery, the universe just doesn't seem to make sense without them. Quarks originally helped explain a torrent of particle physics discoveries that happened after World War II, but our knowledge of particles goes back further than that. Before the war, physicists knew about familiar subatomic building blocks like protons and electrons, and they knew that particles sometimes decayed. Some of those building blocks could transform into other particles, although the rules were still being worked out. In general, though, it seemed like there weren't that many fundamental pieces of matter. The world was pretty simple. But then experiments got better at crashing those pieces into each other and seeing what happened. By 1950, the list of known particles included pions and kaons and sigmas, with new particles being found all the time. Soon there were dozens of types of them, and no one knew why they were showing up or how they might be related to more familiar particles. But throughout the 50s, there were hints at some sort of underlying order. Physicists quickly realized that the new particles were much more like protons and neutrons than electrons or photons. They also noticed that the particles didn't come randomly. There were family relationships. For example, after the pion was discovered, they found a particle that acted a lot like the pion, but had the opposite electric charge. Then there was a third particle that acted like both of those, but had no charge at all. So eventually physicists just grouped them together as positive, negative, and neutral pions. Meanwhile, some particles, like the kaon, took strange-looking paths through particle detectors. So scientists said that the kaon had, and I'm not making this up, a quality called strangeness. And they grouped together particles with strangeness and particles without it. There were lots of other groupings floating around too, with different people thinking different ones were more or less important. But in 1961, a physicist named Murray Gell-Mann took a huge step forward. He found ways of grouping particles together that naturally included lots of the other ways people had proposed over the previous decade. His groups came in a few different sizes, but since they most commonly contained 8 particles, Gell-Mann called his idea the Eightfold Way, after the Buddhist path to enlightenment. Some of his groups were incomplete though. For example, the Eightfold Way said that if you group certain particles by strangeness, the group should have 10 members. But physicists didn't find the 10th member until 1964, a few years after Gell-Mann predicted it. Still, that was a good sign. Once they found that omega minus baryon, as it's now known, everyone knew Gell-Mann was on the right track. Then, around 1964, Gell-Mann and 2 other physicists named George Zweig and Andre Peterman all independently came up with the same explanation for the Eightfold Way's success. Each of the particles was itself made of a few tiny indivisible pieces. Peterman wanted to call the pieces spinors, and Zweig wanted to call them aces, but Gell-Mann had a way with naming things, and his name for them stuck: quarks. By combining just 3 types of quarks, called up, down, and strange quarks, into collections of 2 or 3, you could produce all the particles physicists had seen over the previous few decades. Except for things in the same family as electrons, but those have their own models, and there were only a couple of those at the time anyway. Admittedly though, the quark model did have some weird features. It said that, unlike every particle ever observed, quarks didn't have an electric charge that was a whole number times the charge of an electron. Instead, they had fractional charges, either negative 1/3 or positive 2/3. And that struck everyone as very weird. It was unlike every particle they'd ever seen, but there was a reason they'd never seen fractional charges. Over the next decade, physicists working with the model realized that you could never see an isolated quark on its own. Quarks could only ever be in groups of 2 or more, because there was just too much energy sitting in the space between groups to ever tear them fully apart. Again, it's very weird. But just like the Eightfold Way, the quark model caught on because it worked. It was a simple explanation for complex mysteries. It explained why neutrons, which are, like the name says, electrically neutral, act like they have electric charges in them in specific cases. They're made up of 2 down quarks and an up quark, which each have charges. And it naturally explains strangeness too. Particles with strangeness were particles with strange quarks in them. The real kickers came in 1968 and 1974, when 2 different experiments showed conclusive evidence that the quark model was right. In 1968, experiments at the Stanford Linear Accelerator fired electrons electrons into protons. They found that they bounced off in ways that only made sense if the protons were made of individual pieces like quarks instead of being solid balls of charge. Then in 1974, experiments at 2 different labs revealed a new particle that couldn't exist in the original 3-quark model, which would have been a disaster if physicists hadn't already extended the original model to predict a 4th quark called the charm. Today we know of only 2 more quarks, the bottom quark and the top quark, which were originally called truth and beauty, but apparently that was just too much. And there are good reasons to think that that's it. Our universe has 6 total types of quarks and no more. With just those quarks plus the forces between them and a couple other particles that are cousins of the electron, we can figure out a ton. We can understand the behavior of the hundreds or even thousands of different types of particles that are created all the time in particle accelerators. And that's the kind of simplicity physicists strive for. Ah, physics, it's so beautiful. Just like a good spreadsheet or a really flexible Trello board. I co-host SciShow with Hank, Olivia, and Mike.
All right. And at that point, the content of the video ends. So let's proceed. So some key takeaways from this video, there's of course a historical aspect, but also particles, they can be broken down into the quarks, right? Particles that were originally thought to be fundamental, right? Like the proton or the neutron can actually be broken down into these quarks. You saw sometimes the neutron can act as if it like has that electrical charge in it. So we'll expand a bit on that. So there's a violation of the quantization of charge as well, right? Where there's like, you saw in the video, there's the minus 1/3 charge. There's the plus 2/3 electron charge, right? Instead of just positive multiples of the electron charge. Like you might learn in like AP Physics 1, I know in previous years, they teach the quantization of charge, for example, right? Or we discussed it a bit earlier as well, but that property does not apply in particle physics. Also, you can see there's a strong nuclear force, right? That's why physicists were not able to notice quarks in the past, because there's a very strong binding force between the quarks. And of course, there's also a lab component like Stanford Linear Accelerator that you were looking at. And they were taking like electrons, firing them into the protons and everything, right? And looking at the different collisions, which allowed for quarks to be discovered a bit more easily. So now let's look at some fundamental properties of particles. There's 3 fundamental properties that we're going to look at. We have a property of mass, which is described by relativity, right? In special relativity, we look at E is equal to mc squared, right? And you can see here the particle has mass if energy is required to increase its speed or accelerate it. And then general relativity expands and creates a few new ideas that particles with mass actually produce gravity, right? And they're able to curve space-time, right? Particles affected by gravity, even particles with no mass like photon, right? So any particle with mass is affected by gravity, and even particles with no mass. So then we'll discuss charge. So charge we discussed a lot in the electromagnetism unit. It describes the electric field that a particle can create a certain distance away. It has units of Coulomb, or you can take it in electron charge as well, depending on your application. Sometimes they use even different choices of units, but mainly the electron charge and the Coulomb is used. In particle physics, though, we mainly use the electron charge. Like charges will repel and opposite charges will attract, of course. And you saw different charges, right? Like protons are +1, electrons are -1, neutrons are 0, which are the basics that we know from before, right? But you also have quarks, and basic quarks will have like 2/3 charge and -1/3 charge. We'll elaborate a bit more on that. And there's also spin, which of course a particle is not actually spinning if you think about it. Spin more refers to the idea of angular momentum, or the constant turning of a particle. And for elaboration, there's also a spin number that particles can have. It's a characteristic number for bosons, or half integers for fermions. And so that's the idea of a spin number. Next, we'll discuss quarks. Quarks are a fundamental part of matter, as you learned from before, from the video. And they compose hadrons like protons or neutrons. There's 6 different types of quarks. You have an up quark, which is the lightest quark. And so the up quarks can help to form the neutrons and the protons. And you can see the formulas for those over here. And it's part of what we call the first generation of matter. And the up quark will have a +2/3 charge and a bare mass. This is the bare mass you can see here. Now note that there's the units, right? There's electron volt. This is just energy, right? The mega electron volt is just energy. And it's divided by the speed of light squared. So you can see that you get the units of mass essentially. This is like a relativistic mass unit. It's basically what's being shown here. You can see even from the table earlier, if you look closely, we'll post a bigger version of that, but you can see that there's the units of relativistic mass in here. Let's proceed. And there's also spin of 1/2. All quarks have spin 1/2. The down quark is like an analog to the up quark. It's a bit heavier, also a major constituent, and you can see it from the neutrons and the protons. And you can kind of do the math on here. There's a charge of -1/3. So you have the neutron, right, which is 1 up quark, 2 down quark, is 2/3 minus 2 times 1/3, gives you a 0 neutral charge. And then you have protons, 2 up quarks is 2 times 2/3, which is 4/3, minus a 1/3 for the down quark is a positive 1 charge. So it does work out, the neutrons and the protons. And you can see there's the bare mass of the down quark. And the down quark will be the second lightest. And it's also part of the first generation of matter. Let's continue to 2 more types of quarks. We have from the second generation of matter now, you have the charm quark and the strange quark. And so charm is the third most massive, and it forms more complicated types of hadrons. Sorry, I was having some Zoom issues a while ago. Let's continue. So we have different hadrons, like the different kinds of mesons you can see, as well as baryons. We'll elaborate a bit more on that. And you can see it has an electrical charge of plus 2/3 E. And the bare mass is 1.275 plus or minus 0.04. Note that it's in giga electron volt now, right? So this is a lot bigger than what we had before in terms of the bare mass. So you have giga electron volt divided by the C squared. And you have spin 1/2 as well. And similarly, you can group the strange charge in that third generation, right? With strange quarks found in hadrons. And there's different types of hadrons in here as well, like kaons, different types of mesons and baryons, and other what are called strange particles, right? And you were looking at the property of strange before. So like different particle detectors, the kinds of behaviors that were happening because of the presence of the strange quarks. These are part of second generation of matter. It has electric charge of minus 1/3 E and a mass of 92 mega electron volts, but spin 1/2. Let's continue now to the third generation of quarks. Third generation of quark is like top quark and bottom quark. And top quark is the heaviest quark. It derives its mass from coupling to the Higgs boson, which we'll talk about in more detail. And in the standard model of particle physics, it's the strongest coupling, right? And you can see different properties, like the spin 1/2 and an electric charge of 2/3 E. And it's the heaviest, as you can see, another giga electron volt, which is close to, this rhenium is like, it's like number 75 atomic number on the periodic table. And if you check your periodic table, you can see that it has 186.21 AMU, or a gram per mole. And you have the bottom quark as well, which is another third generation quark with minus 1/3 E charge. And you can see that the mass is around 4.18 giga electron volt, which is still pretty heavy, not as heavy as the top quark, of course, but still 4 times the mass of a proton and much, much larger than light quarks like the up quark or the down quark. And so you can look through a lot of these different ideas and different properties of the quarks. One thing to note is that a lot of quarks in very short amounts of time will decay into first generation quarks, which are up quarks or down quarks. Like these things, top quark, bottom quark, merely last like a picosecond, right? Like 10 to the minus 12 second or on that order. So these particles decay very quickly. Next, we'll discuss the nuclear strong force. Nuclear strong force is one of the fundamental forces of physics, and it's responsible for literally holding the universe together. Why is that the case? Because it binds the quarks. It binds the quarks into protons and neutrons. And so we have this thing called color in quantum mechanics and particle physics, right? Which is about quantum states like red, blue, and green, which are not actual color. They're just different quantum states. And colors can be changed via gluons, which are exchanging quarks. And so if a quark goes like far away from other quarks, for example, the quark will go far away, right? Then this actually becomes stronger due to the force carrier of gluon. And the quark gets pulled back, right? And so it's able to stay together in proton or neutron, right? And so we can expand a bit more on this. And also the pion becomes involved as these high energy interactions occur as the gluons are being carried, right?
Then we also have the nuclear weak force, which is another one of the 4 fundamental forces. This force is responsible for radioactive decay. And whereas like the strong nuclear force is governed by gluons, the weak nuclear force is governed by W and Z bosons. And these particles have very heavy mass, and so they move slowly and only at low energies, hence they're named the weak force, and why they interact with lower energies, and that's why they do radioactive decay. And so again, it is a weak force. It is constrained to only the distance of 1% of the average atomic nucleus. So yeah, that is it for today for our introduction to particle physics. Thank you for coming, everyone.
All right, we'll try to get a few more resources to you guys pretty soon. Thank you so much for coming, everyone.